Hi AP Psychology students, and welcome back. Today we are continuing our discussion of sensation, which is topic 1.6, but we are moving on to focus on the sensation system of hearing, also known as your auditory sense. So we're going to be focusing on learning objective 1.6c, which is explain how the structures and functions of the auditory sensory system relate to behavior and mental processes. And we're going to do that by answering these three essential questions. So first, how does the transduction process work in the ear? Second, how do differences in parts of the auditory system impact our hearing? And third, what theories explain how we differentiate and locate sounds? Okay, so auditory transduction, just like visual transduction, involves the same processes, right? We have stimulus energy, the anatomy of our receptors, turning into a neural impulse, and then the brain, right? So just a quick overview of those parts of the transduction process. So what does this look like specifically for our auditory transduction, right? So auditory stimuli are communicated through sound waves. Sound waves are very similar to light waves. They have two properties: wavelength, which determines the pitch. This is usually referred to as the frequency, measured in hertz. So if you think of like something really, really high pitched and squeaky versus something low pitched and kind of like a deep tone. And then there is the amplitude, and the amplitude determines the loudness of the sound, and this is measured in decibels. So something that is very loud has very high decibels, and something that is quiet or soft, the decibels are lower. Okay, so a little bit about the anatomy of the ear, right? Obviously, we have this sound wave that's entering the ear, and really, when it comes to transduction process, we focus on the anatomy of the ear, starting from the middle ear to the inner ear, right? So, first of all, that sound wave enters the ear, goes through the ear canal, and vibrates that eardrum, sometimes called the tympanic membrane. It's the same thing. So it vibrates the eardrum, and the eardrum then vibrates three small bones in the inner ear that are called ossicle bones. So they have individual names. You'll see them listed on the diagram, but really you can just think about them as a whole set of bones called the ossicles, and they are the three tiniest bones in your whole body, right? So if you ever happen to need that information for trivia, and they vibrate in response to the vibration from the eardrum. So the sound wave hits the eardrum vibrates, the ossicles vibrate, and the ossicles carry that vibration to the cochlea, where the cochlea is basically the retina of the eye, the cochlea is of the ear, right? So here's where we get a difference that can happen between people. So damage to the middle ear, so damage to the ear canal, but specifically the eardrum, any of those bones kind of getting fused together, or any kind of other damage that can happen to those parts of the middle ear. That's where we have what's called conduction hearing loss. So that's hearing loss that's caused by the fact that the sound wave cannot be conducted to the cochlea, where then it's translated into a neural signal. So I mentioned the cochlea previously, but the cochlea is this fluid-filled tube in the inner ear. It is pronounced cochlea, not Coachella or Coachella, although it can be helpful to remember because you think of Coachella like the concert, cochlea, they sound the same, right? And the music and hearing, so it can be helpful to remember, but it is pronounced cochlea. And the cochlea is what contains the receptor cells. So just like I said, the retina in the eye, the cochlea in the ear. And then from the cochlea, it goes to the auditory nerve, which then takes it up to the thalamus, and then to the temporal lobe in the brain. So let's focus a little bit more on the cochlea, right? So the cochlea, like I said, has it gets the vibrations from the ossicles and the eardrum, right? So the sound goes in, it vibrates the tympanic membrane eardrum, vibrates those ossicles, and then those ossicles send the vibration to the oval window, which is where kind of the vibration forces then fluid inside the cochlea to move, right? And that movement of the fluid inside the cochlea then stimulates these little teeny tiny hair-like receptor cells. They're called cilia. They literally look like hundreds of thousands of little hairs, and they bend, kind of like thinking about grass kind of bending in the wind, right? They bend as a result of the pressure from the oval window. So like the vibration happens, and then the fluid moves, and the hair cells bend, and that bending tells the hair cell to send the message. So like where the bending happens is where the sound is kind of transduced. And generally, if you have damage in this part of your ear, so a lot of this damage happens naturally through age and like loud sounds and this kind of thing, this is what we call sensory neural hearing loss. So you can see the difference between the hair cells in this normal picture versus the hair cells in this damaged picture. And the thing about hair cells is that they don't grow back. So, if you burn your tongue, those cells are damaged, but they like regenerate fairly quickly, a day or two. Your hair cells do not grow back. And so as you lose them, you start to lose different frequencies in your hearing because they're no longer able to transmit or transduce the sound. Okay, so we've talked about the stimulus energy, which is sound waves, the receptors in the ear, changing to neural impulses in the cochlea, and now we're on the brain. So just remember that auditory nerve takes it to the thalamus, which sends it to the temporal lobe. Okay, so a little bit more now on the theories of sound. So we talked about how the transduction works, but how does your brain actually know what sound you're hearing? Like, how does your brain know if it's a high pitch or a low pitch? How does your brain know if it's a clarinet or a oboe or a trombone or whatever, right? How does your brain kind of organize and understand the sounds? So the first theory of this is called the place theory. And this is the theory that every single place in the cochlea, right, that you can see in this diagram right here, every single place in the cochlea is responsible for transmitting different hertz or different frequency levels to the brain. So for example, a sound wave that enters in, at the top here and kind of bounces at the 700 hertz or 7,000 hertz or 5,000 hertz, etc., that they would be transmitted to the brain at that place, and that would tell the brain, oh, it's a frequency of 5,000 hertz, that's this sound. You can see that it goes from like 20,000 hertz at the beginning kind of to 7,000 hertz pretty quickly, and then the rest of the membrane kind of breaks down quite like softer from there, right? We go to 7,000, 5,000, 4, 3. So what we know is that high sounds, or high pitch sounds get kind of vibrated at the very beginning of the cochlea, which is why oftentimes people hear, lose those hearing frequencies first, because they get the most damage from the sound waves coming in kind of consistently. And this theory best explains high-pitched sounds. They actually find that if they are looking at it inside the cochlea, there is a very specific place where a high-pitched sound hits the cochlea, and that's how your brain knows the different pitches. However, this does not explain low-pitched sounds. So what we found is that low pitches tend to vibrate kind of like a huge chunk of the cochlea all at once. And so it's harder for the ear to maybe differentiate different sounds within lower frequencies. So what this theory tells us is that the frequency theory is that different nerves fire at different rates, and that those rates match the frequency of the tone. So if you look at this diagram here, what I'm showing you is that A would be the firing of the nerve, and B would be the frequency that came into the cochlea. So if you see that the nerve actually matches the firing of the frequency of the sound. So, and this is really helpful for low pitch sounds, except there's a problem because your nerves can't fire more than 1,000 times a second, and you have higher frequencies than 1,000 hertz. So then they also find that there's this add-on to frequency theory, which is the volley theory, where cells kind of alternate to fire, like fire, 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 and that then they like gets added together in your brain. It looks a little like this. So like cell 1, 2, 3, 4, 5, 6 all fire like in succession, but what happens is your brain kind of sees them firing as one message, and so then the frequency of firing is much faster than if each one just fired by itself. And this is called the volley theory, kind of like volleyball, like fire, 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 like back and forth to add together to create greater frequencies. So those are the major theories of how we know what frequency of sound we're hearing. Now, the next question is, how do we know where sounds are coming from? So with this theory, we use something called sound localization. And really what this theory tells us is that there's a reason we have two ears. So sound waves strike one ear before the other, even if it's just a quick moment of difference, and that helps orient us to the location of the sound. What this also tells us is that when sounds happen in front of or behind us, top of or below us, and hit both ears at the same time, it can be very difficult to place that sound without your visual cues. So obviously, if a sound is coming from in front of us and we see the stimulus that's causing the sound, like a fire truck or a person talking or whatever, it's very easy to tell. But if you have your eyes closed and you don't know where the sound is coming from, it can be very difficult to know if it's in front of or behind you because they hit both ears at the same time. All right, so today we talked about the transduction process and the anatomy of the ear. We talked about some differences that can lead to impacts on our hearing, and we went through the theories that explain how we differentiate and locate sounds. So that's all for now, AP Psychos, and remember, psychology is flippin' awesome.